Okay, so we are on question 1.2 from Regression and Other Stories. So here's the question. But basically, in the chapter, we're given this plot right here, and we're told, and we can kind of verify it for ourselves, that that the regression line right here is given right here in the picture. So y equals 46.3, so the intercept is 46.3 plus 3x. Okay, and so we can kind of verify this. So for the intercept, it's a little bit misleading because the x-axis goes below 0, but if we go to 0, which is where the intercept is measured at, and we go up, here's the line, and I could be argued into believing that's 46.3. And then if I go up 1 unit in x, okay, so from here to here, from 0 to 1% along the x-axis, so from here to here, I could be argued that that's about 3 units up on the y-axis, okay? And so that's the regression line. Okay, so now we're asked to sketch some different lines. So y equals 30 plus 10x in both cases, but in one case we have a standard deviation of 3.9, and the next one we have a standard deviation of 10. Okay, so we could just draw the lines. If we have, so we could just draw these two lines, right? So and we also want to sketch the data. So by sketch, I'm going to actually simulate the data in R, okay? And so that's what we'll do here. So first I'm going to simulate the first regression line, or the first regression and data. So with this, it'll have this regression line with a standard deviation of 3.9. So in order to simulate the data, I need to kind of make, I need to make a y and an x that kind of correspond to all of this, okay? So I'm going to throw a few little flourishes into the code just for fun here. Okay, so first I need to simulate data. So I have x, okay, so I'm randomly simulating 16 data points because that's what we have in the graph that was given to us. And I'm simulating data from 0 to 4, right? We're supposed to go over the same range as was given in the previous problem, or in the previous graph. So we go from 0 to 4. Okay, so that's what I've done here. I've simulated x values. And then we want y values that have an intercept of y and then a slope of 10. Okay, and then a standard deviation of 3.9. And so I've created y variables in two different ways here. They're equivalent, but I just wanted to show two different ways. So the first way is I have the systematic component here, right? So 30 plus 10x, which corresponds to this. And then I've added the standard deviation as being from a normal distribution with mean 0, right? So our error in a normal linear model has an expected value of 0, of mean 0, and then it kind of moves around that with the standard deviation. And the second way that I've done that, I'm calling that y2, and again, this is equivalent to y1, but I'm simulating, or I'm putting the standard deviation into my expression for the slope, okay? So these are just two ways of doing it, okay? And now I'm actually going to regress y1 on x and y2 on x. So I've generated this data that should correspond to the equation that we're supposed to use, and now I'm actually running regression on that data, and then I'm going to plot that data, okay? And so I'm going to have two sets of data in two lines, right? I'm going to have data for y1, data for y2, and then I'm also displaying the formula or the equation of the lines that were generated by the two regression coefficients, okay? And then this is in a for loop here, so we'll display 4 different plots. That's just to kind of give you a sense of the sampling variation. So when I go through this, let's just look at these plots here, okay? So again, I have kind of 2 sets of data on each of these generated from the same process. I have the black dots are y1, the red dots are y2, and I have my 2 regression lines, okay? The solid one is y1, the broken red one is y2. Again, these are just equivalent. These are just different samplings of the same data generating process. And then we have the formulas up here, the equations that are found actually, okay? So again, we're supposed to be at y equals 30 and then the slope at 10, and you see that they're both about 30, and the slopes are a little bit weird here, but you know, they're both around 10, okay? And the extent to which these aren't exactly 30 and 10, that is just sampling bias, okay? So in other words, that deviation just comes from the fact that we randomly sampled data from the data generating process. Okay. So again, here's another plot, and you can look at the intercept and coefficient, and we just did this 4 times. And if you were to run this again, you would get 4 different plots. Okay. So now next, we want to do the same thing, but now with a standard deviation of 10. The code is basically identical, except for now, you'll notice that the standard deviation is 10. Okay. So if we run this, we get our different plots. Okay, let's scroll to the top here. So notice a couple of things. One is that because of the larger standard deviation, there's more distance typically between a data point and the line. And I've also had to expand I maybe overdid it a little bit, but expand the range of the y-axis here, right? Whereas up here we were going from like 20 to 75 or something like that. Here we're going from about 10 to 100, right? That's to accommodate the larger spread in the data. But again, you can go through these, look at the coefficients. I would predict that if you were to do this a bunch of times and then look at the difference between the estimated intercept and slope, that this model would tend to would have more deviations from 30 for the intercept and 10 for the slope than would the previous one. And that is because the larger standard deviations mean that the data is going to spread out a little bit more, so there's more room for kind of poor estimates of these intercepts. Okay, okay, that's it.